talking will happen during that thing, and so let me explain what I'm going to talk about. This is joint work with my student Soumaye Jalili and my colleague Mohsen Khani. And okay, so I'm sorry, just okay. So I think the general idea is to study Frasse-Hrushevsky construction method outside stability and simplicity realm. We know that this kind of construction, by this construction, we had lots of good examples or counterexamples for certain conjectures within stability theory or simplicity. But I think the general question is how far we can, push these constructions to get something really good outside stability or simplicity. So possibly one way of looking at this problem is to see what sort of sufficient conditions one can find for this, like what John calls ab initio. That's just to find some kind of interesting ab initio constructions in which you could get Frasse-Hrushevsky limits with, say, Nib theory or whatever you like in a stability hierarchy. So that sounds a little bit difficult question, but the other more approachable question probably is to see how much these kind of construction are well behaved with respect to certain operations like bicarbonate expansions or fusions, and to see whether these kind of operations, well, I mean, how much you can transfer, let's say, NEAP or NSOP1 or NTB2 from the theory T or T1 or T2 that you start with to the fusion or the bicarbonate expansion. That's the idea. And in this talk, I will concentrate on bicarbonate expansions. So I'm talking about bicarbonate expansions of geometric theories. Certainly, there are two sources for this kind of construction. First is just the Frasse-Hrushevsky construction about bicarbonate fields in which we consider expansions of algebraically closed fields, say strongly minimal theories with DMP, by some colored predicates, either a predicate for coloring of a general set, which we call it black fields, or some additive subgroups, which is called red fields, or there's some multiplicative groups, subgroups that are green fields. These kind of construction are aimed to very specific questions about, let's say, finding bad fields or something like this. But the second approach and the second way of thinking about this is called what we usually call lovely pairs, extension of models by a reduct, and things like this. I think in the second approach, more or less, the study is more abstract, that you could start with a very general theory of geometric theory, and you just study, the problems that I mentioned in the beginning, and you see that how much you could axiomatize the expansion, or how much you can transfer stability hierarchy to the expanded language. I'm sorry that I don't name anyone here. There are many names that we should mention, but I fear to skip some names, so I rather not to name anyone here. But there are many names that we should mention here that work in these areas. But our approach somehow, from a methodological point of view, is related to first approach, but this, our somehow point of view is more abstract, like the second approach. So as usual, we start with a countable language L, and suppose T is a geometric theory, which means that it eliminates the quantifier that exists infinity many, and the algebraic closure operator gives rise a pre-geometry. That means that the algebraic closure has the exchange property. So, and for convenience, we assume that theory T has quantifier elimination. Of course, this comes for free because you always can consider an expansion of theory, definitional expansion like Pourmahdian, something like this, that to consider theory T satisfies the quantifier elimination. Okay, and as T is as theory T is geometric, there is a notion, well-defined notion of dimension, in which you can attribute and you can associate a natural number to any tuple, as we call it, dimension of A bar, which is the number of cardinality of maximal independent subtuple of A that's independent. And also similarly, we can define dimension of a set. And also we can define dimension of a definable set by taking the maximum dimension of tuples that satisfies this formula. So, and you have some nice properties such as definability, that's the sets, the parameters that whose dimension sets over with respect to phi is exactly k, this set is definable, L definable. And also you have kind of wedge definability, sorry, I mean this infinite conjunction definability, which roughly means that you can just define dimension of x over y is at most k is you know, infinitely disjunction definable. Of course, what I wrote here is not exact, but exactly if you want to have an exact statement, we should say that given two tuples A bar and B bar, then you could find a formula inside that you know, that type, which exactly states the dimension is at most k. So, and also the dimension function induces the notion of independence, which we denoted here like this, and you know, can be defined as usual by stating that any finite tuple from set A, if you take any finite tuple, then the dimension of A bar over C is the same as dimension of A bar over C bar, and the dimension satisfies the usual you know, condition like symmetry and transitivity. We here we impose some kind of natural condition on T in which our construction can move forward. For example, I mean, the first kind of condition that we consider, I call it free amalgamation property, which means that if any substructures sits inside two models of T, which are algebraically closed inside M and N, then you can amalgamate M and N in a model freely, which means that you can have, you can sit, you can this here, and you can find an amalgamation here. Basically, that these two sets
so should it be M1 and M2 above in the?
Oh yes,
F1.
yes.
Should F1 go?
Yes, exactly. Sorry, yes. Here, yes. A and A. Yeah. Let me just, here is M2. That this is correct, right? This is you put M1 and 2. Yes. You're right. And M2 here. Yeah, exactly. It means that outside algebraic closure, you can freely, I mean, you don't need anything to identify other than algebraic closure. This is very natural, and many natural examples do satisfy this condition. And it's easy to see that free amalgamation implies that the dimension independence has the extension property in this sense, that you can find anything that satisfies P of X and is independent from A over B. This is needed really for basic construction to do it, in this kind of amalgamation. Other condition, which seems a little bit more technical, which we call it indecomposability. A T is indecomposable. Exactly means that algebraically closed sets of dimension M cannot be written as a finite union of algebraically closed sets of smaller dimensions. Like for example, if you consider vector spaces and over a field, over an infinite field, certainly this is an obvious condition. And the condition is really needed for axiomatization that I'm going to give later. And this is somehow one of the implication of this indecomposability is that given any set of dimension M, you could find and if you give me an N and you require to find an N a finite set with N elements whose every M elements are still independent, that's doable. So this indecomposability gives you the way of finding large sets still have every its elements are forms a basis for that set. And I'll explain why this is needed. So once we define this, the condition for T, we can define Bicarbonate expansions. So Bicarbonate expansion is nothing but adding predicates, which we call it the coloring predicates, and we fix a rational number between 0 and 1. It is strictly bigger than 0, but it could be 1. And we take the LP structures and LP expansions, LP structures like this, which M is a substructures or models of T, and we define a pre-dimension function, very usually defined and by this, and this is the dimension of A minus alpha times the number of colored points or black points. Here we are in the context of black, which means that we are just having arbitrary set. And we require,
black is without structure, is it?
Sorry?
It's without any structure on the predicate, black point, right?
Right. Yeah. No structure. It's just black points. Meaning that you name an arbitrary set, not a subgroup or something. I mean, just arbitrary subs.
Okay.
And you require that you take the subclass by taking those structures with whose any finite subset has positive pre-dimension. For example, if X happens to be in algebraic closure of empty set, to be in this class, a point in this class, it means that delta of X should be dimension of X minus alpha times P of X. So this is 0. So if this want to be positive, it means that X cannot be colored, or it should be white. So here, unlike the this in the context of generic expansions by predicates, we require, and the axioms and the class force us to have non-colored algebraic sets, and another word, predicate P should include only transcendental elements. Okay, delta alpha is a pre-dimension, so it's just very classic things and folklore things that the delta alpha is submodular, and and we can also define the relative pre-dimension like things everywhere. I mean, this is just classical things that I'm reminding. Nothing special. And once you have the notion of pre-dimension, you can define the notion of closed substructure by requiring that any finite subset of n, when you take its intersection with M, should have a relative positive pre-dimension. For example, meaning that if you have M here and N is here, and you take some points, finite points, and some finite points here, always the pre-dimension, relative pre-dimension of these points should be at most, it should be positive. And so this is called, the conditions that just forms a smooth class, meaning that it has this kind of conditions that you can see here. It's just very natural conditions that is like usual substructure or elementary substructure. For example, this one usually when you consider for elementary substructure is called Watt-Tarski condition. And also the last condition, which is very crucial in a condition which allows us to define the notion of closure. So you're dealing with some kind of maybe we can also view it as an abstract elementary class, but you have the notion of closure, which means that for given set X, you can always have, there exists smallest set containing X, which is closed in M. So intersection of closed sets that includes X should be also closed, which basically comes from the last condition I mentioned above. So and free amalgamation, free amalgamation property means that implies that the class K plus alpha with this notion of substructure has the free amalgamation property. I mean, it has amalgamation property plus it's free, which is freeness with respect to this kind of pre-dimension that you can define. And as always, you could consider empty structure as a particular structure in K plus alpha. So JEP is a special case of amalgamation property. So as this class has AP and JEP, therefore you would be able to take the lambda homogeneous models in this class, which are called either generic or Fraser limits or Londa-Rich, or I mean the different contexts they name like this. Let me just notice that unlike the usual amalgamation, Hrushevsky amalgamation method, we do not consider to have a countable generic structure or rich structure. So you might still have some omega rich structure, but not countable. So we do not require the class to have countable generic structure, but still the methods you could produce lambda universal models like abstract elementary classes like this, and you could just take these structures by general construction. And so the aim is usually to study this axiomatizing Londa-Rich structures. Okay. Now to understand the Londa-Rich models, I will shortly introduce a theory T alpha, T sub alpha, which gives an axiomatization for Londa-Rich models. And the approach we are choosing here is just Laskowski's approach to give, in the case of Shelah and Spencer random graph, he gives a simpler axiomatization for this kind of graphs, and we use basically his methods to give the axiomatization and the conditions that I mentioned. I mean, namely indecomposability is because of having this method work for our context. So that's why I restrict myself to only the indecomposable theories. So let me just give you a brief explanation of what is the theory T alpha. It's somewhat very natural in a sense that you impose conditions which you can express them in a first order way. Certainly theory T alpha should include theory T itself, and also should require that the models of this theory should be inside the class K plus alpha. So this also can be done and can be stated because of that infinite definability I mentioned. And the most crucial part is to give an axiomatization for, the how to find points inside model once you have a strong tuple like this. And here we have two, in some previous slide, I defined two types of important closed structures that I'll mention. Let me just briefly mention them. here, we have two important type of extension. First is algebraic extension, meaning that B is algebraic extension over A if all elements of B are algebraic, whereas B is transcendental if all elements of B are transcendental. So, of course, you could imagine that you have a mixed, kind of hybrid condition or mixed condition, but nevertheless, you could, for any A and B, if A is strong in B, you can find some, B1 in which B1 is algebraic over A and B is transcendental over B. And in that axioms that I mentioned now, we are dealing only with transcendental. That's what we can, do it. And the point is, once you could handle and settle the transcendental pairs, you could the theory itself and the closures would give you the algebraic extension. So, and here you'll see that stating that if you yes.
Sorry, I have a question about this second axiom. So
right.
The dimension here is still the geometric dimension.
Yes, exactly. Yeah.
Each element in the tuple is not algebraic, but it's kind of algebraic over A overall. If K is strictly less
it's K. Yes. It's not algebraic over A, but still is not. There could be its dimension. It should less than n. I mean, it could be that like this. Yes, exactly.
Okay.
And phi is an L formula. You see here, phi is an L formula, and here is just. But once you're stating that, well, I mean, this strong formula is something technical. I don't want to define it, but once that if you have a formula like this, and there exists some tuples which is somehow transcendental over Y, and its dimension is the right dimension, then you could find a tuple which satisfies this formula plus the coloring is like the colors of the same as colors at D, which certainly is a very natural and it's usually you'll find, and because of the definabilities, all such materials are definable, and these are classical things, but for special, the things that you should add up here is that you should deal with strong formula rather than any formula, and also require the dimension to be K, which all can be done in the first way.
So,
yes?
Sorry, Massoud.
Yes, please. Okay.
Axiom, how is K quantified on the
K is fixed. K is fixed.
It's fixed and is fixed. So you ask this axiom for all.
Yes, and you
for all pairs
A and D. Exactly. A and D are given. K is given. Phi is given inside the, somehow this formula is inside, A and D. Yes, and in the quantified free diagram of A, these are given, and you're stating this formula. Okay.
Well, okay. I'm not completely sure I understand. How is D? D is a fixed. What is D?
D.
So
no,
you.
I mean,
so there is a connection between the index of D and the index of X, right?
Right, and you have a diagram is given. I mean, this is the axiom schema, which is related to this. You have.
But is it, for instance, if the dimension of X over Y is n, Is it the same as a generic predicate? I mean, do you ask like you can put whatever zi, a solution of phi in
yes,
P or not in P?
Exactly. But if the formula, but I mean, here is something which is kind of weaker, is that you require that phi xy is strong. As strongness means exactly something that you can find nominate some tuple. I'm sorry, I mean nominate x to y in a way that once you attribute some associate some color to x bar, then the delta of x bar over y bar is positive. Okay. This is different from in the case of generic predicates. That's the certainly. But the point is, you don't need. I mean, the axioms is somewhat similar to what is given by Chris Laskowski, that you don't require that this Z to be closed or enclosed or something like this. That's the point here. And obviously, we should first check whether this T alpha is consistent. But the good thing is that omega-1 rich models always satisfies T alpha, so T alpha is a consistent theory. But on the other hand, when you want to study the the completeness, you should consider irrational and rational alpha separately. So okay, that's why you should consider rational alpha.
Massoud, I think the problem with your microphone, sometimes it gets very loud.
No, okay. Now how about now?
Now it's good.
Maybe its connection is not somewhat non-smooth. So okay, I'll try not to move that much. Yes, okay. All right. So yeah, and in the composability of T, I mean, for irrational alpha, what you would need, what we should prove is that, I mean, the technical part to prove that the completeness, we need these technical things that you need. Once you have a transcendental extension of A, you could find D star containing B, which is still a transcendental extension of A, but its pre-dimension, relative pre-dimension, is very close to A as much as we want. I mean, this mu is just some approximation, and it's possible to do it by considering indecomposability of T. That's possible. But still, D star is enclosed, but I mean, depending, n is given, and then you can find very large extension whose relative pre-dimension is very close to A, yet you have some nice properties like this and like this. This is really technical things, but that's what I'm just mentioning important parts. And okay, so for irrational alpha, to prove the completeness, we found somewhat easier to adapt the Baldwin-Shellot approach to adapt the notion of semi-genericity here, and show that any omega-1 saturated model of T alpha, first of all, is semi-generic, and then using more or less the same methods that they give to prove, I mean, with more, more careful look at, the things like types and notion of closure and the things that are generated by these things, because you are dealing with T, which is not you might have some closure that is you might have some substructure that's generated. It's not like relational language that you're dealing with sets. So you should really be careful in working with these kind of things. And once the notion is settled down correctly, we are able to prove that any two semi-generic models are elementary equivalent. Therefore, T alpha is complete. And for irrational alpha, somewhat life is a little bit easier, and still for transcendental extensions, you must find that extensions, which in which here we can find D star to be 0. I mean, the relative predimension is 0 exactly, nicer than irrational alpha. And we don't really need here to consider semi-genericity, something like this. It's just directly, we can prove that any omega saturated model of T alpha is omega rich. And as two omega rich models are back and forth equivalent, therefore, the theory T itself is complete. So nevertheless, in both rational and irrational alpha, we have in monster model, types are exactly described by the isomorphic type of closure of the substructure that's generated by the closure of A. That's more or less coming from either the semi-genericity in the case of irrational, or coming from omega richness directly. Let me just mention that in the case of irrational alpha, closure of finite set might be infinite, but still countable. But finite closure of finite sets, in the rational case, finite sets have finite closure, but not uniformly bounded though. So okay, so that we are now more or less now in a situation to prove the main result here. We are just focusing on NIP property, and the thing is that we are able to show that if T has NIP, then so does T alpha. So we can transfer not independence property to T alpha itself. And also, when alpha is rational, T alpha, and T alpha is strongly dependent, T alpha is also strongly dependent. Whereas if alpha is irrational and if T defines a linear order, then T alpha is not strongly dependent. So these results resembles in the case of ab initio examples that, when you are working with rational alpha, the theory of generic is omega stable, whereas when you are working with irrational alpha, the theory is strictly stable. So here, I think we somehow from this point of view, we can see that the theories differentiate between rational and irrational alpha by this by the mode-theoretic property of strongly dependent. So a strongly dependent can differentiate between between rational and irrational alpha. Okay, I think I have just maybe in the remaining time, I just explain the main ingredients of the proof, though I should be very sketchy. Okay, so I think that strategy that we are following is to prove that the number of co-heirs is at most to the power of a cardinality of m. So this is I think this is the way that we rather to use the global proof of NIP rather than going and analyzing the formulas, which somehow we need to take the notion of d-independence, which is attached to, I should have written here d alpha, but in order to be, so given any pre-dimension delta alpha, we can take, d-independence, and as usual, in this construction, nothing special here. So I just reviewed here this one, this structure, and the point is, okay, so the independence that's defined here has this property. I think this is a crucial property here, that two tuples are d-independent over y if their closures are, first of all, d-independent in the sense of T, which I mean that algebraic independence, and also the closure, the union of two closures are closed, meaning that the closure, the union of closure is exactly a closure of A bar and B bar over Y. So that's the importance of the independence here. Now, to prove the theorem, first we should note that if type of A over C is a co-heir extension of type of A over M, then first of all, type, you could add more things to the A bar, because the closure of AM itself is a subset of algebraic closure of AM. So still you have type of closure of, I mean, this is a very big and infinitary, I mean, not big, I mean, small, but still, but infinite tuple is a co-heir extension of type of closure of AM over M. And the other important things and ingredient is that if you have a co-heir extension, this extension should be d-independent over M. This is very important, that the co-heir extension implies d-independence. In the case of irrational, we are able to prove that something stronger, that the dividing independence implies the independence, but for irrational alpha, our proof only works for proving co-heir extension is stronger than the independent, which is enough here. And okay, and once you have this, okay, and so since it's d-independent, type of A bar over C is determined by L type of this infinite sequence. So here is in LP type, here is the L type. here just a bar, but here is something bigger, maybe infinite, but its closure is at most, I mean, the cardinality of this set is just bounded by M itself. So, and it's obviously if A bar is a co-air extension type of A bar, where C is a global type, is co-air extension of type of A bar over M, then the L part, the L type of this is also co-air extension. So that means that if you, I mean, counting the number of co-airs over global co-airs over M, it amounts to counting the number of, you know, L co-airs of these sequences over C. But as T is NIP, still we could have, you know, this number to be bounded by 2 to the power of cardinality of M, and that's why you're able to prove, you know, the NIP property for that. And I think I'm kind of out of the time, so just mention that strong independence for rational alpha, we can follow the same line of definition and check everything. I mean, this is very nothing special here except for understanding the definition of DP rank and following the proofs. And but I should mention here that so according to DP rank terminology, the DP rank of theory is Aleph 0 minus. We are not, we do not prove that even when you start with some, let's say, ominimal structure, you do not get something like finite DP rank. So, and the point here is that although closure of finite set is finite, but it's not uniformly finite. So maybe if you adapt the construction and modify the construction by taking uniform finite closure, that might be possible to prove that the resulting structure is or has finite DP rank. But here we do not have this property. And also we need to have T to have a linear order, or is unstable rather. This is the part of our construction. So let me just conclude my talk by some questions, saying that, okay, so what about other stability conditions in the stability hierarchy? So how about NSOP1, NTP2, simplicity, and other things that do these conditions transfer to T alpha? And also the other interesting question could be, study red and green things in the style of Frasel-Hrushevsky construction, and but here also you could have kind of some issues regarding axiomatization, like modal rank property, things like this. And so these are interesting questions to think about. And also the other question is that how about taking bounded DP rank? And this seems interesting questions, and these are for interested people to consider. Okay. All right, so thank you very much for your attention. I think this is more or less what I wanted to say. Okay.
Thank you, Massoud, for your talk. Are there any questions in the audience?